Hello everyone, hope you enjoyed your coffee. And now let's get started with, I think, the third graph databases talk of this day, which means graph databases are getting more and more important, which is a good thing. So, and my talk will be about scaling of graph databases, because that is a pretty hard problem that we had just in the talk before already, and I will just go into more details in there. A little bit about me. My name is Michael. I'm from Germany, especially Cologne, and I'm working on a graph database which is called ArangoDB. And there I'm actually team leading of the graph development. I have been responsible for the web frontend, now that I handed that over, and I have pretty much invented the smart graphs that I will cover in this talk. Good. A little bit of repetition. What are graph databases? Typically, graph databases store two things, vertices and edges. Vertices are schema-free objects, so you can store arbitrary loads on vertices, and then you have edges which form relations between these vertices that you have. And typically, edges have a direction. But edges can be queried in both directions. So I can say, please go backwards in the edge, or go forward, or I don't care, go both ways. That really depends only on the query. It does not depend on the way you store the edge. And graph databases are extremely good if you have to query ranges of steps. So something like, I need to go 2 to 5 hops from my starting point, which is super hard to formulate in a relational database. And even you can do an undefined number of steps. You can say, start here and go as long until you find the target position. And you can combine shortest passes between two random points in your graph, without even knowing how many relations are in between, or if there are any relations that really form this path. So what are typical graph queries? So queries that you should ask a graph database and where they are fast at. Typical, easiest one, please give me all the friends of Alice. That would be one relational hop. We can do that in a relational world as well. Give me all the friends of Alice. So 2 steps away. But please include all the ones that are in step 1 already. So like triangles, and then the third one is excluded. Or given Alice and Bob, what is the linking path between them? Or if I'm at a vending machine at my train station and it tells me you can go up to 6 stations from now on, and I have no idea where I can go, then I can just ask a graph database, please give me everything I can reach within 6 steps, changing as many trains as I like. But the major thing are pattern matching queries. So I define a subgraph which has some certain properties, and I want to find all instances of this subgraph in my graph database. So give me all the users that share 2 hobbies with someone called Alice. Or classical recommendation, which sounds pretty complex, but give me all products that at least one of my friends has bought, together with the products that I already own, because then it's most likely that I need them as well. What are non-typical graph queries? So queries you should not ask a graph database if you want to have performance. Give me all the users which have an age distribution between whatever, 21 and 35. Because that is actually really bad for graph database which is focusing on this traversaling, so going alongside the relations. This is something that you should ask a relational database or a document store, because it just uses the attributes on a certain object. Or just do an aggregation, give me the age distribution of all my users. Or group all their users by their name, because the names are, again, attributes based on one of the vertices. And that is why, and that is because graph databases typically have this traversal optimized. That is the query mechanism underneath where you which you actually execute whenever you ask a graph database. And I'll just do it as an example. And I want to iterate down 2 steps and would like to apply some filters based on the edges. And what happens then? I have to pick one start vertex, which is called S, and then I stand there. Then I have to take a look at all the connected edges for S. Then I have to check which of these edges actually fit the filtering conditions. So in my case, I would like to exclude this edge. Then I still have S to A and S to B. And now I just have to pick one of those two, so either A or B, and do the same step again. So for A, get all the connected edges, then apply the filters on these edges. So in this case, throw away the edge to D. And then, if I would do more steps, I would now go to E and again do the same thing. But as I only do 2 steps, now I have my first pass that matches my traversal query. So now I can return S to A to E. And then I have to go back the whole pass, so I'm standing now at E. I go back to A. Are there any edges that I haven't processed yet? No, so I go back to S. Are there any edges I haven't processed? Yes, I go to B. And then, again, the same thing. Ask B for all its edges. Only one found. Apply the filters. In this case, the edge matches my filter. And then I found my next result. So next pass S, B, F. And then again, go back. And then go back to S, which has no other edges anymore. So I'm done with my traversal. Let's talk a bit about complexity, because we had it in one of the talks before that graph databases are pretty performant if you ask the right queries. And that is because the traversal complexity does not depend on the size of the entire database that you have. It just depends on the things that you actually visit. So once you have to find the start vertex, so the starting point of my traversal S in that case. How fast I can find it depends if I can use an index. So in the best way I use a hash index, then it's constant time performance. I can find one start vertex to start the traversal. But then, for every depth I define, I have to execute 4 steps. First of all, I have to find all the connected edges. I can either do that with an edge index or with index-free adjacency. What's the difference is will be coming later in the talk. Typically, this is constant time performance in both cases. So this pretty much doesn't cost anything. But then, I have a set of edges. And now I have to walk through these set of edges and check first, does my edge match the filter? This is linear in the amount of edges, so typically complexity n. Then I have to find the other part of the edge, the other side, target vertex. Then again, I use the same index that I could use on top here. That can be a hash index in the best case, or a sorted index, then it's logarithmic. Let's assume we have a hash index. Then this again, I have to do this once for every edge, n times 1. And then I have to take a look at the vertex as well and check, okay, does this vertex match the filter conditions? And only then I can return it. But all of these can be done in one go. So one pass, 3 times n for every depth. And now comes the problem. Depth 1, I find 3 times n many additional edges or additional vertices, starting points in the worst case. If I do depth 2 now, that means I have to do this again. And then I have complexity 3 times n square. But it's not that bad. So linear sounds evil, yes. But it's not linear in the amount of all edges that I have. So I can store billions of edges, doesn't matter, as long as for every node I only hit 10 of them. Then it's not a problem at all. And therefore traversals solely scale with their result set size and not with the entire database size. And there is a famous theory which is called the 7 degrees of separation. That is pretty much true for all natural networks. So networks that are formed by people, for example, or by nature. And that means just pick any random 2 persons, let's say me and Barack Obama. And now find all the intermediate persons until I'm connected to Barack Obama. So I know you, for example, you know the other one, and this one knows Barack Obama. And the theory says at most 7 people in between for the shortest pass. And that means if I do a depth 7 search in a natural network, I will take a look at all the vertices that I've stored. and that will be super expensive. It would be better to do a different query in that case. This is not true if I artificially generate my graph, of course, so if it's not naturally born, but if I include a lot of stuff in there with some relations, then this may not be true. Good. As I'm doing some live sessions, I have to introduce the technology that I'm going to use, and that is ArangoDB. And ArangoDB is a so-called multi-model database, which allows to store documents, graphs, and key values just in one single technology. It's completely open source, so we are on GitHub. You can just download it and look at the code. We have one query language called AQL that covers all the data models that we have. So you can do document queries, graph queries, joins, and all of them in the same statement. So you can start with some document stuff, continue with some graph stuff, and then finally combine it with some key value lookups. And we have asset support, including multi-collection transactions. As I've talked about AQL, I'll just give you some short examples because that would be the queries that I'm going to execute. So AQL looks a bit like programming. You always start a for loop, and then you define for some variable in a collection. A collection in our terms is comparable to a relational table. So it has a lot of data rows. And then I can return something. So in this case, I just return something that I find, which is a JSON document. I can combine it with filters. So check for attribute values inside these documents. And as promised, I can do graph traversals. So first of all, I start with a document query for user and users, select the user with name Alice, and now I want to find out which products Alice has bought. Then I just say for product in outbound direction, because I just want to go in the direction of the edge, starting at the user using the collection has bought for the edges. And of course, I can make it arbitrarily complex. So I can do the complete recommendation query in a simple string. So recommendation action is the last edge that that goes to the product, and the entire path. And here I'll just say, please go 3 steps, ignore the direction, apply some filtering on the passes, some limit, and then return the recommendation that I need. Good. To show you that it actually works, I have, is it readable? So I have a small data set on my local computer having the American airports and the domestic flights of 2 or 3 months stored in the edges. And the simplest query is I just try to find an airport, and then I can just find all the airports that are reachable from this starting airport. So SFO is San Francisco, for those of you who don't know. So target in one outbound step, starting at this airport. Return. Okay. I have to do something. So I can, in addition to this one step outbound or the traversal, I can modify it. So the traversal that I've explained earlier was depth first. So I just go the depths down until I cannot find anything anymore. The alternative is breadth first, where I just start at my S, then look at all the neighbors and work on all of them, and then look at their neighbors and work all of them in the same way. So I first start with depth 1, then with depth 2. And it's guaranteed that I do not find anything in depth 1 after I started processing depth 2. I will do this here. And I would say unique vertices global, which means I will just visit each vertex once during my traversal. So I can directly make a distinct query. And if I execute this, I misspelled something. I think return is actually fine. And expected near. Of course, I have to define which edges I would like to follow. So, and here we see it takes me roughly 0.4 seconds to compute all the all the airports that I can reach from San Francisco. And that took into account all the flights that are between those airports. And there are multiple flights per day. That's why it takes a bit longer. Good. Now let's talk a bit about performance optimization. So how can I get graph databases to be running faster? So you remember the complexity? 3 times n to the power of depths. And filtering of non-matching edges is linear for every depth that I have to do. And the issue that we have are so-called supernodes. So supernodes are those nodes that have lots and lots of edges going out or into this specific vertex. And San Francisco Airport is, of course, one of those. There are a lot of flights going from San Francisco. And something that we can do to improve the speed on supernodes are so-called vertex-centric indices. That are indices that index all edges based on their starting vertex or their target vertex, plus an arbitrary amount of other attributes. And that means I can find the initial set of edges in the same time, because the index is as fast if I just search for the single vertex or if I search for something more. But I have less or no post-filtering anymore. So therefore, I reduce the set of edges that I actually traverse to take a look at. And this decreases the amount of n in the terms of my complexity. So how does that look like? Let's go back to the query. So first of all, I need to add a filter condition to the passes so that we actually see a difference. Therefore, I need to use the pass, and I then just say for filter pass edges star day of month. So my query will now be that I would like to fly on 1st of January, or 4th of January, sorry, which is 4th day of month. So I would like to fly on 4th of January, starting in San Francisco, and I'm willing to switch planes 1 time. So in 1 to 2 outbound steps. First of all, I have to filter the day of month, 4th, and I think I need all of them should be on the 4th, because I do not want to wait a day at an airport. And then I think it's month equals 1st, which is the January. And if I now execute this query, it takes some time. I think I did a mistake. Just give me a second. Path edges. Day of month and here I forgot the all. So, but never mind. This query takes some time, so 1.6 seconds. And if I now go to the collection and say, please now use an additional index, which is based on a hash index, so I want constant time lookup, which is using the from value, which is using day of month, and which is using the months. So all the 3 values that I give in my filter are covered now by the index. And off we go. There is an index, and we see in the selectivity estimate the edge index, just using from or to, is pretty bad, and this index is a bit better than the edge index. And if I now execute the same query, and off we go, below 100 milliseconds. Just because I use good indexing, and now I could cover the supernode San Francisco in reasonable time. But this is still running on a single machine. Now let's talk a bit about scaling. So vertex-centric indices help with supernodes. They also help in a distributed environment, of course. But what if my graph is too large to be stored on a single machine? That means I have to distribute my graph on several machines, and this mechanism is called sharding, because I chop my data set into shards and put them on the different machines. But how to query it now? So first of all, I have no chance to get a global overview of the complete graph, because that does not fit on my machines. And what about edges that are linking between vertices on different servers? Those are the problems that we are actually facing when we have to shard, or if we have to shard a graph. But let's first do this cluster thingy. And there I would like to introduce you to a nice tool, which is written by the company of Mesosphere, and that is the so-called DCOS stack. So it consists of 3 parts. Apache Mesos has to be installed on every machine. And this figures out how many available RAM you have, how many CPU processors you have, and how many disk space you have. Then you have Marathon, which runs somewhere on these Mesos things, and can talk to them, and figures out, okay, in total we have in this cluster 330 terabyte of RAM, distributed across all these Mesos slaves. And Marathon actually allows you to start processes, which figures out, okay, you need 8 gigabit of RAM. There is one machine which has these 8 gigabit free. Schedule the service on this machine, which is pretty nice. And the cool thing is, whenever this machine dies, the Marathon knows, oh, there was this process running, and started somewhere else. So you do not have to worry about it. It will just restart the process somewhere else, so it's not lost. And DCOS is an additional UI on top of that, which allows you to manage the resources, to take a look, okay, where are the bottlenecks, where is the performance going, and has a cool app store where you can just install sharded applications directly into this Marathon framework. ArangoDB is one of these things that are in their app store, but you do not need this Mesosphere stack if you want to run ArangoDB. So then you have to do some manual effort for the setup. So you have to execute a script there where you just say, okay, these are the servers which are playing together in a cluster, and that's basically it. What you get then is automatic failover. So whenever a shard in ArangoDB dies, one of the other takes over who has a copy of this data. You can rebalance the shards across the servers if you add new ones, and everything inside ArangoDB, of course. And what we did with Mesos is that you have a complete self-healing cluster. So they figure out, okay, this instance is dying, there was an ArangoDB running, we just spawn a new one, we'll connect to the cluster and copy everything over that it needed. Good, but now let's distribute the graph. What are the dangers of sharding? So first of all, only parts of the graphs are on every machine. I do not have a global overview anymore. Even worse, neighboring vertices may be on a different machine. And even worse, in some graph databases, it can be that the edges connecting these 2 neighbors on different machines is lying on a 3rd machine, making it pretty hard to actually find out where everything is and to make the query correct. Therefore, queries need to be executed in a distributed way, and the results, which are smaller than the entire graph, need to be merged locally. There are actually pretty much 2 ways to distribute the graph inside a cluster. First thing is the random distribution. So I just, for every object that I have, I throw a dice and put it on one server, depending on the result of the dice. The advantage is every server takes an equal portion of the data, so all of them are filled to the same amount. It's super simple to implement and to realize. Doesn't need any knowledge about the data. It always works. Disadvantages: it's most likely that the neighbors are on different machines. Probably the edges are on either different machines than their vertices. So therefore we have a lot of network overhead required for querying, because the graph in memory looks like this. You cannot figure out, okay, where was which part and how is this connected anymore. But as I told you, it works, and ArangoDB can do it. So I have prepared a cluster of machines where I have just used a so-called a social network, which is called POCAC, which is available in the Stanford University, so you can just download it. And I have inserted it twice. So first in the random distribution, which I want to show you now. So every profile is somewhere, every edge is somewhere, and probably somewhere else. And now I execute a simple query. I just want to find friends of friends, so 1 to 2 depths. But the first friend should be of age 36, and only 100 of them. Where is the error? I think I made a mistake somewhere. Let's just reload. Okay, demogods are not with me. So 1.6 million docs are there. Relations. Okay, somehow the relations got lost. Yeah, loading. So those are 30 million edges, if I'm not mistaken. And I hope no one has killed my cluster. It's doing something. Okay, there we go. So actually I find 50 friends of friends in roughly 3 seconds. So let's just do it again, so that it's not some loading in between, which was not finished. So, okay, 3 to 4 seconds that I need to actually find all the friends of friends. But, okay, it's slow, but kind of works. So now I can scale my graph basically unlimited ways. But it's not fast. So how can we get this thing fast now? First of all, let's talk a bit about index-free adjacency, because index-free adjacency is advocated by most other graph database vendors as the one and only thing useful for graph databases. And it means that every vertex maintains 2 lists of edges itself. So basically the inbound and outbound edges to a certain vertex are stored directly at the vertex. They do not use an index to find these edges because they don't want it to slow down. But the problem is, how can I shard this? So one part I can shard easily because those are connected. The other parts I can shard as well. But what about this edge? Where should I store it? Should I store it on the left server or on the right one? ArangoDB uses an hash-based edge index, so we still have the same complexity, constant time. But this allows us to store the edges independently of the vertex. So we can actually decide, just put it on the left one or on the right one. It doesn't matter, because the other one can just figure out, okay, I have to ask the other server because there's the edge. And because of this, we are actually able to use a different type of sharding for graphs. And that is what we call domain-based distribution. So because many natural graphs have a distribution in their nature. So for people, it's more likely that you have friends in the same country. And it's unlikely that you have a lot of remote friends. So therefore, sharding a graph based on the living country of persons is a pretty good idea. If I'm storing blocks in a graph, then it's probably a good idea to shard them based on the on the tags, because mostly blocks with the same tags are somehow connected. And if I'm doing some e-commerce stuff, then it's probably a good idea to shard the graph based on the category of the products. And this is something that most of our customers at least know in their application. So they know there is this one attribute that actually separates the graph pretty good. And we would like to use this domain-based distribution then. So, and the idea is that most edges are in the same group, and you have only rare edges that are in between those groups, so that you can cover large parts of the query on a local server, and only seldomly you have to switch servers in between computations. And now you actually see, okay, these are pretty good graphs by themselves. And here we have these rare cases where the edge actually does not have a vertex on this machine, but the vertex is somewhere else, which is an expensive case. And the enterprise version of ArangoDB uses this domain knowledge to shard the graph correctly and for shortcuts in the traversing queries, which allows us to actually get very close to local computation time, even for sharded graphs. And to prove that, I will just go back to the interface. This is the same dataset that we have, but now I will just use the domain-based version, which is called smart because we called this feature so-called smart graphs. I just use a different graph, so the different collection, other sharding, other graph name, and hopefully the edges are now there, and off we go. 0.1 second. In comparison, where's my mouse? Here. The other one did use about 4 seconds to compute the same result. And that is because the graph is sharded pretty good already on one machine. And therefore we can just get large graph scaling with performance. Good. Then we have made an additional benchmark, which is a bit old now, and we are doing the next version right now, where we actually want to compare to all the other vendors out there. So this graph, so this benchmark is actually made on a single server because the other vendors, or some of the other vendors, do not allow to shard at all, especially Neo4j. There's only a single server, or the complete graph at least has to be in a single server instance. And we are a so-called multi-model database, so we expected that we are like pretty close to the specialized solutions, but the specialized solutions could be a bit ahead of us because they only have one data model to focus on. But it turned out we're actually better than that. So for single read operations, which is something that you typically very often use on a database, MongoDB is a bit faster, so MongoDB is a document store, and Neo4j as a graph database is pretty slow on that case, because that's not a typical graph query. They are more focusing on starting at one point and then searching around there. And as we have this multi-model capabilities, we actually have focused on improving these things as well. What did astonish us the most is that for the graph features, like shortest path neighbors, we're actually way faster than the specialized graph database Neo4j. And another competitor, OrientDB, is, as well as we are, a multi-model database. So they have the same ideas, but I think technically we are a bit ahead of them. What you pay with ArangoDB right now uses a bit more memory than all the other ones, because we have in-memory hash indices, but that will change with the next version that is in our pipeline. Good. Thank you very much. Do you have any further questions about graph databases? Then please feel free. Thank you. Good, any questions? There. Just wait for the microphone, please.
So if you plan to reduce your memory requirements by going away from in-memory hash indexes, how will that affect the speed, and how do you intend to achieve it?
So actually we are not only going away from hash indices. We are exchanging the storage engine that we have underneath, which is right now memory mapped files, and we replaced that with RocksDB. So then we have something which does not eat up so much memory, but is still comparably fast. And then we will have in-memory or partly in-memory, so hot set in-memory edge indexes on top. So that means the performance is hopefully not much slower, but we do not exceed the RAM limits anymore. So that is our long-term plan for the next release. Because then with these indices, we have the hot set feature, which allows you to actually do what you query the most, which is in RAM, and the things that are somewhere outside in the borders of the graph, which you do not query that often, those have to be get from disk, which is then slower. But in typical ways, the query performance should be the same. Further questions? Nope? Ah, there. Wait for the microphone, please.
Do you keep any other sort of statistics that let you optimize your query plans? For example, looking at nodes with a small number of potential vertices of particular type first.
So we keep some statistics to optimize our query plan. We do not, let's say yet, sort the edge index based on this amount of outbound edges, but that is something that we consider to do in the future. Right now we do not use it, but we use other parts, so estimate which index is the best, so because each index can determine how many documents it will find roughly, and then we pick the best index. But if we have this list is not sorted by any kind, which would be an improvement as well. Good. Another one. Sure.
I just wanted to ask, what would be some typical example customers of ArangoDB? So what would be a good kind of requirement set where you might consider using you?
So ArangoDB is always good if you need to do some, let's say, polyglot persistence. So where you have multiple different data models in your application, but you do not want to set up 6 different databases. Then ArangoDB is a good one because you just set up ArangoDB and store all the data models in one core using the different query language features. And you do not have to replicate parts of the data between the document store and the graph store, for example. So let's say the classical e-commerce system where you have a product catalog which is pretty well mapped into a document store. And the recommendations, you need these relations because the document store cannot join properly. Then you actually need one document store, one graph database. And you can either pick 2 and set both of them up and share some parts of the data, because whenever you do some recommendations, you need some parts of the products. Or you just use a multi-model database like ArangoDB, where you only have it in one source, and you don't have to replicate between those different technologies. And of course, for everything where you would use one specialized one, you could as well consider to use ArangoDB, because that gives you advantages on the long run. Whenever your CEO comes around and says, I have this pretty awesome idea, we should add some social features, and suddenly you need a graph database in addition to the document store you're using. Yes, please.
Sorry. The smart graphs domains sharding looked pretty snazzy, but it looks like it's in the enterprise edition. Can you achieve some of that in the non-enterprise, presumably free edition?
No, you can't. So the complete optimization to execute everything locally is secret in the enterprise version, which is not open source. Because
Thanks.
yeah, it's not needed in community products where you typically do not scale like beyond terabytes of data. Because as soon as you have this amount of data, it's only fair to actually buy the enterprise version. Good. Thank you very much. And whoever likes, I have some t-shirts.